So number 7, I actually think this is the hardest one on the worksheet. So in this one, we have a cell that's suspended in a solution of glycerol. So here's glycerol. And the cell has sucrose inside. But sucrose cannot cross the membrane. However, glycerol can. So it says, what changes would you expect to see as diffusion and osmosis occur? So first, let's talk about our solutes here. So our glycerol can cross the cell membrane. So what we're going to see is glycerol is going to go into and out of the cell. And because glycerol is starting off only on the outside of the cell, it needs to reach equilibrium. So it's going to reach equilibrium by dividing in half of this 0.3. So after a little bit of time, instead of having 0.3 glycerol outside the cell, we'll have 0.15 molar glycerol outside the cell, and also 0.15 molar glycerol inside the cell. That's where glycerol is at equilibrium. Now, sucrose cannot cross the membrane. So at this point, our solutes are not going to be moving where the concentrations are changing. So now I want to think about what that does for water. So for water, if I take a look at my solutes, outside the cell, I only have 0.15 molar solute. Inside, if I add my sucrose and my glycerol, I have 0.3 molar solute inside the cell. So that means my concentration of solute inside is high. So high solute, remember, means low water. So I'm going to draw my L because I'm always going to label water when I'm talking about osmosis. Outside the cell, I have 0.15 molar total. So this would be low solute outside the cell. So that would give me high water. So I'm going to label outside the cell as my H because, again, I'm going to label my H and my L as water. So what is water going to do in osmosis? Water is going to enter the cell because it's going to go from high to low. So let's check off to the side what's happening. Glycerol, it's entering the cell, but so then that means the next one can't be true. Sucrose cannot move across the membrane. So sucrose is not exiting the cell. So that would be this box. And we decided because there was high water outside the cell and low water inside the cell, the water is going to enter the cell. Okay, so question number 8 says, assume that the above cell and solution reach equilibrium. Draw the concentration of glycerol and sucrose that we would see. So I kind of drew that up top, but let's just clean it up. So outside the cell, we have the 0.15 molar glycerol. Inside the cell, we have 0.15 sucrose, because remember that couldn't move. And then we have the 0.15 molar glycerol that did enter the cell. So now it says label the cell in the solution as hypertonic or hypotonic. So inside the cell, we have 0.15 plus 0.15, so we have a total of 0.3 molar solute. So inside the cell, we have high solute. And when we have high solute, remember that is hypertonic. So our cell is hypertonic. Outside the cell, we only have 0.15, therefore that would be low solute. So low solute and high water, that's hypotonic. So we have a hypotonic solution and a hypertonic cell. Okay, so let's define some of these terms that we had in our notes yesterday. So turgor pressure, my first thought is that's in a plant. And this is where our plant cells have water entering. And because of that cell wall, When they enter, they're going to swell and get a little bit firm. So remember how we talked about how the plant gets wilted, but then when you water it, it stands up straight. That's because of turgor pressure. Plasmolyze. This was another term for our plant cell. And this is when water leaves. Lyse. This was our term for animal cell. And this is where water enters our animal cell. And for whatever reason, it's not on there, but I think it's a good time to go ahead and review the term crenate. And this is where water is leaving an animal cell. So now we get to practice these examples, and we're going to label whether the solution is hyper or hypotonic and then predict what's going to happen. So if we take a look, the cell to the left, if we take a look, I'm going to label or think about how 0.9 inside the cell is greater than the 0.5 outside the cell. So in this case, I'm going to label the cell as an example of, because it's higher inside, the cell is hypertonic. Now, we need to think about it in terms of the water now. So if the cell is hypertonic, that's high solute, so low water. So outside is high water, so water is going to enter the cell. And because the cell is circular, it's going to be an animal cell. And the term for animal cells that increase in size, that is lyse. Okay, for the second one, we can see that we have a higher concentration of the solute outside the cell than we do inside the cell. So the cell would be considered hypotonic. And now if we go through and label our water, because inside the cell has low solute, it's high water, and outside would be low water. Therefore, water is going to exit the cell. And because this is an animal cell, that's going to make the animal cell shrink. And remember, another term for the water exiting the cell and what happens instead of shrink, you could also use the term crenate. All right, so now let's look at some plant cells. You can tell they're plant cells because they're rectangular. And if we take a look, our concentration is higher of our solute inside the cell. So the cell has high solute, so that would make it hypertonic. And then if we're thinking about water, water would be high outside the cell, low inside the cell. So water is going to enter. And when water enters a plant cell, that then increases the turgor pressure. And it becomes turgid. So probably you see the pattern, but let's talk about it anyway. For the last one, you can see our concentration is higher outside the cell than it is inside the cell. So we have a low concentration of solute inside the cell. So the cell is hypotonic. And one more time to label, that means low solute, high water. Outside the cell, we have low water. So water is going to exit the plant cell. And when this happens, we call it plasmolyze. Okay, here we have a graph similar to our potato lab, but it's not so obvious here. So I just want to highlight, this is my 0. This was my x-axis. And what was super important is we wanted to find that point where it crossed the x-axis. So I'm just going to estimate about where that is, draw as straight of a line as I can, and see where that ends up. So let's go ahead and answer some of these questions. So it says, a student was trying to determine the sugar concentration of a potato cell. They hypothesized that if it's placed in various concentrations, the potato chunks either gain or lose mass based off of osmosis. So here it says potato chunks are going to gain mass whenever things are moving into or out of. So if I think about if it's going to gain mass, that's what sticks out to me first. So it's going to gain mass when water, because remember, we're always talking about the movement of water with osmosis. It's going to gain mass when water moves into the potato cells. And if we think about why would water go into, we can draw a little picture for ourselves here, right? If we have like the beaker and we have our little potato chunk, right? Why would water go into? So it would go into if the concentration of water outside is high and the concentration of water inside is low. And water concentration would be low inside whenever we have a high concentration of solute inside. So therefore, we would have a low concentration of solute outside the cell. So that would be called a hypotonic solution. The next one, I noticed that these potato chunks are going to lose mass. Why would they lose mass? They would lose mass because water is leaving the potato cells. So why would water leave the potato cells? Let's draw ourselves a little picture. So we can have that water is going to leave when the concentration of water is high inside and the concentration of water is low outside. So why would the concentration of water be low outside? Because we have more solute outside, therefore my solution must be hypertonic. So when are potato chunks going to stay the same? They're going to stay the same when it's placed in an isotonic solution because water and solute are not moving in and out. So I actually don't like any of these, but it's the water. And I would change that water is moving in and out of the cell in equal amounts. That's what equilibrium is, when water is moving equally in both directions. So it says, use the graph above to determine where this is. So if I go back to my picture here, I best estimated right in between 0.2 and 0.3. So my estimate is going to be at 0.25 m for my concentration of sugar.